This lecture reviews the birth of a star. This spectacular image of the Lagoon Nebula illustrates many of the aspects of image interpretation the modules about stellar measurements explained. The caption reads, "Stars are forming even today in the new Lagoon Nebula. This bright nebula is visible in the constellation of Sagittarius with binoculars. The above photo is a result of a new sensitive camera being attached to one of the world's largest telescopes. Curtains of collapsing hydrogen are shown above in green, highlighted by a special filter that isolates light from this specific atom. Many young stars are evident in the open cluster M8 in the lagoon, the result of previously collapsed gas clouds. Many of the stars appear red because of the high amount of dust in the Lagoon Nebula. Red light penetrates dust clouds best, although enough dust will block all visible light and leave a dark nebula. The mass of the nebular cloud that forms a star determines the mass of the star. Here are two images from NASA of the pillars of creation in the Eagle Nebula. The image on the right is taken in the infrared, showing that the dust of the image to the left is penetrated more readily by light in that region. The pillars of creation in the Eagle Nebula captured in infrared light by Hubble. The light from the young stars being formed pierced the clouds of dust and gas in the infrared. Kant reasoned in the nebular hypothesis that diffuse nebulae, dim clouds of dust and gas, that were only first being well observed in his lifetime, would collapse under the force of gravity, forming stars and planets. This process of gravitational collapse also formed the sun and the planets. In the nebular theory, a cloud of dust and gas broke into rings, each ring condensed to form the sun or planets. The nebular theory is an evolutionary theory where the formation of the solar system occurs with a series of gradual and natural steps. A modified form of the nebular theory is still in use today, but the collapse of the nebulas to form stars takes a long time. Pearson's textbook breaks down the process of star birth into 7 stages. Gravity causes the cloud to collapse, and the clouds break into smaller clouds, which can further fragment into even smaller clouds. In this model, a single cloud does not give rise to a single star, but a cluster of stars. The sun and all other stars we see formed in clusters, not necessarily the same cluster. As the cloud fragments, the minuscule spin they started with begins to increase as a consequence of the conservation of angular momentum. At each stage, the outward radiation pressure balances the inward gravity. As the cloud collapses, the plasma becomes more dense and its temperature and pressure increase. The star has become a protostar, and it can now be plotted on the HR diagram. Protoplanetary disks have protostars embedded in them, seen on edge, as in figure A, or on face, as in figure B, and can be found in the images of star-forming regions. These dust-filled disks may evolve to form planetary systems. Examples of protostars are the T Tauri stars. Protostars also go by the name young stellar objects. Here are several examples: T Tauri V1307 Ori, HK Ori, V633 Cas, RR Tauri, and V633 Cas. Notice all of these objects are associated with remnant dust clouds, leftovers from the star's formation. The mass of the star determines its initial position on the HR diagram and its progression to the main sequence. Protostars are huge, so they enter the HR diagram towards the upper right, where very cool objects, but very large. The protostar's large size and low temperature makes them bright red objects. There are 3 possible outcomes, all based on mass. The largest stars travel nearly at constant luminosity toward the main sequence. Smaller protostars become smaller and less luminous when they reach the main sequence. All during this protostar phase, the pressure and temperature of the core of the star increases. When the core temperature reaches 10 million Kelvin, hydrogen burning, that is proton fusion begins, and a star is born. The smallest protostars, with masses less than 5% of the sun's mass, do not reach the critical temperature for fusion and are failed stars. They are called brown dwarfs. In 2014, Kevin Luman announced that using data from the Wide Field Infrared Survey Explorer, also known as WISE, a brown dwarf now named WISE 08550714 was discovered and found to be 2.23 parsecs. That's 7.27 light years from Earth. As of 2014, it also has the fourth largest parallax, 449 milliarcseconds, of any known star or brown dwarf. Hence, it is the fourth closest extrasolar system to the Sun. It is also the coldest object of its type found in an interstellar space, having a temperature between 225 to 260 Kelvin, which is about negative 55 to 8 degrees Fahrenheit. Brown dwarfs have many elements in common with stars, but they lacked the mass required to have fusion processes take place in their core. The discovery of these brown dwarf stars by WISE in the Spitzer telescope made Sheldon Cooper's "Stars Nearest to Me" song incorrect. There are now known stars that are closer than those stars. NASA's Spitzer Space Telescope and WISE Telescope are satellite-based infrared observatories. They are important for learning about star-forming regions and protostars. Spitzer detected tiny green crystals called olivine, thought to be raining down on a developing star. An arrow points to an embryonic star called HOPS 68. It is located in the dark filamentary cloud of cold dust and gas. Over 5 light years in length, located just north of the Orion Nebula, which is seen here as the bright region at the bottom of the image. The remainder of this lecture explains one way that infrared light can be used to measure the mass of protostars. It is not part of the core material of this course and can be skipped if you're in a hurry. If not, sit back and enjoy a back-of-the-envelope physics calculation. The information in the next few slides is directly quoted from Space Math at the Goddard Space Flight Center from material they provide for educational outreach. This is an image taken by the Spitzer Space Telescope in the infrared part of the main electromagnetic spectrum. Instead of seeing the light from stars, it sees mainly the light from heated dust grains in space, glowing with temperatures between 100 to 200 Kelvin. These bright young stars are found in rosebud-shaped nebulosity known as NG67129. The star cluster and its associated nebula are located at a distance of 3,300 light years in the constellation Cepheus. A recent census of the cluster reveals the presence of 130 young stars. The stars formed from a massive cloud of dust and gas. Most stars in our Milky Way galaxy, including our own sun, are thought to form in such clusters. Most of the infrared light comes from a deeply embedded protostar called Fur-2, which produces 430 times the total power of the sun, with a temperature of about 35 Kelvin. We can use this to estimate the mass of the nebulae. The next few slides show how to measure the mass of the nebula, and are for informational purposes. You are not going to be required to solve problems like this on tests. A single dust grain is about 0.2 microns in diameter and has a density of about 2 grams per cubic centimeter. What is the total mass in grams of this dust grain if it has a spherical shape? Recall that the volume of a sphere is 4/3 times pi times the cube of the radius. The mass is the product of volume and density. Putting these together, we find the mass of a grain of dust is on the order of 10 to the minus 14 or 10 to the minus 15 grams. Previously, we've used the power of the sun quoted in watts, and that the solar luminosity is 3.826 times 10 to the 26 watts. This is equivalent to 3.826 times 10 to the 33 ergs per second. What is the total power produced by this infrared source if the power of the sun is 3.8 times 10 to the 33 ergs per second? Use the information they gave that most of the infrared light comes from the embedded 35 Kelvin protostar, which produces 430 times the total power of the sun. In other words, the luminosity of this protostar is 430 solar luminosities. So we're just solving for 430 solar luminosities in units of ergs per second. We get 1.6 times 10 to the 36 ergs per second. A single dust grain, 0.2 microns in diameter, at a temperature of 35 Kelvin emits about 7 times 10 to the negative 13 ergs per second. How many dust grains are needed to produce the infrared power observed from the protostar Ch12? To find the number of dust grains, just divide the total emitted power by the power emitted by one dust grain. We find that there are on the order of 10 to the 48 dust grains. What is the total mass of dust grains involved in producing the infrared light from Ch2 in grams? What is the total mass of the units in What is the total mass in units of the sun's mass, which is 1.9 times 10 to the 33 grams? Multiplying the mass of a single dust grain by the total number of dust grains shows that the mass of the protostar is on the order of 10 solar masses. NASA Space Math notes that the actual dust mass has been estimated as about 6 solar masses by several researchers, including C. Eroy in 1998 and Muzzaroli in 2004. The largest uncertainty in the problem is the size of the dust grain and the infrared radiation power emitted by the dust grain. This problem assumed that the dust grain size is typical of what is found for interstellar dust grains, but in the environment of the protostar, dust grains' sizes are expected to vary due to grain growth. Also, the reflectivity of the dust grain depends on the composition and size in a very complex way. By mass, the interstellar medium consists of 99% gas and 1% dust grains. If the gas within Ch2 has the same composition, what is the total mass of the interstellar medium within the Ch2 in solar masses? The answer is found trivially. If the 10 solar masses is only 1% of the total mass, then the total mass is 1,000 solar masses. The collapse of nebular regions and the formation of stars is an active area of research in astronomy.